In this brief introduction, process control, we want to understand product quality specifications and process capability. And that is, we'll learn how to calculate the process capability indices CP and Cpk. Then we want to understand what are control charts that we use to plot product quality, plot the exponentially weighted moving average of quality, and how to calculate a CUSUM. Here we're showing a standard normal or Gaussian distribution of a product quality measurement. And so we can see that we have a mean or average of the product quality measurement. And as we go to lower and lower quality or higher and higher quality, we have fewer and fewer of products in that range. So we're going to assume we have some Gaussian distribution of product qualities in the discussion today. So the process capability makes use of specifications that we have on product quality. We'll usually have an upper specification limit and a lower specification limit related to either product purity or some type of product property like burn gasoline, like that. And so we're going to have a range of acceptable product quality attributes. And then process capability is the range of the natural variation of the product quality attribute. So here what we're showing is a specification of the lower limit and the upper limit. Neither one of these are being satisfied. So we see that we have off-spec on the lower specification limit. We have product that does not meet that. And similarly, we have off-spec above the upper limit. So here we have high process variability, so these specifications are often not met. On the other hand, on the upper right-hand side, we see that the way we've specified the lower and upper limits, then that all the time we're going to meet the specifications. Now, finally, on the bottom plot, what we're showing is we have a pretty wide range of the limits that we desire, but what we see is we still end up with some off-spec product because we have a substantial probability that the lower limit is not going to be met. So first capability index that we're discussing is the process capability ratio, or CP. And what that is the specification range, that is the upper limit minus the lower limit divided by 6 sigma. And remember before that we had with 6 sigma, we should specify a very large number, 997 or so out of 1,000 points, or should be within that plus or minus 3 sigma range. In any event, we want this process capability ratio to be greater than 1. Here's a problem. Here's an example where we actually have that ratio greater than 1, because you can see the upper limit minus the lower limit, the width of it is greater than 6 sigma, but yet we still have product that's not meeting the specification. So obviously a CP greater than 1 doesn't really tell us the true quality control problem for this example where we have asymmetry. So the next one we're looking at is the process capability index, CPK. And so notice that's defined as the minimum of the mean minus the lower limit divided by 3 sigma, or the upper limit minus the mean divided by 3 sigma. And so this CPK, the minimum value of those, should be greater than 1. And so the nice thing is that indeed does handle this asymmetry problem, because in this particular case, the mean minus the lower limit ends up being less than 3 sigma. Therefore, CPK is less than 1. Indeed, we're showing that we have a substantial probability that we're going to have off-spec product. Now, control charts are used to plot a variable like product quality as a function of time. And then we include both the lower specification limit and the upper specification limit on those plots. So the example we're going to present in the next slide is medical grade oxygen purity, where we have a lower limit of 99% and an upper limit of 99.5% purity for the oxygen. And so you can see here over 50 different samples, all those samples between the lower specification limit and the upper specification limit. And the mean value of the purity is 99.21. So that's between the 99 and 99.5%. And our Cp and Cpk indices are both greater than 1. So we're in spec and we would call this process under control. We're continuing to produce satisfactory product. Now the next slide is going to show what happens later on in the process. So after 50 sample times, it's clear that something has happened. So the separation device has had a problem with it. Maybe there's a fouling in the heat exchanger. Any number of things could have occurred. We're not addressing what caused it. We're identify that indeed there is a problem. And you can see at roughly the 59th sample or so, suddenly we're violating the lower specification limit. So that becomes clear from the control chart. And when you look at this entire data set of 100 samples, then you find the mean is barely above that lower limit, but both the Cp CPK values are less than 1. So it's clear then that we're no longer meeting the performance of the process. Now notice that this is fairly noisy in terms of these samples. So often what is done is a type of filter is applied known as the exponentially weighted moving average. And so here we're showing that we have a quality measurement at the kth sample time. We multiply that by a tuning parameter, and then we use a previous moving average and calculate then the updated moving average. And so you'll recognize this is very similar to a first order discrete time filter that we'll often use when we're solving discrete control problems. And so when we apply this to this example, it smooths out kind of the noisy product property measurements. You can see you kind of follow the same trajectory. There's always a little bit of lag, but it is nice to have the smoother presentation of those weighted average values. Now, CUSUM is calculated as just this difference between the specification and the target, and that is summed up over time. So ideally, if you were close to the target, then you would stay close to a value of 0. But once you start from the target, then the CUSUM will start moving quite rapidly from 0. And so here's the case for the previous example on the oxygen purity, that we're staying relatively constant. That CUSUM term is not changing for a large number of samples up until, after roughly the 55th sample. Then you can see that it starts to kind of take a nosedive. And so the fact that there's such a rapid change in the CUSUM metric tells you that there's some problem with this process, that you're suddenly not producing the product up to the desired specification. So to summarize, I should note that the limitation to this talk is that we focus purely on univariate examples, just single measurements of quality. And so we need to use different techniques once we have multiple quality measurements that are involved. But we looked at the process capability indices and discussed specifying the upper and lower specification limits. Then we went and looked at control charts, plotting product quality, the exponentially weighted moving average of quality, and then calculating and plotting the CUSUM.